Okay, this is Unit 3, Lesson 3 in Algebra 2. Today we are graphing absolute value equations using our transformation rules, and we're going to really come to recognize what vertex form is. So far we have graphed using a table of values, and I know that all of you do not always love using a table of values, even though it should be kind of second nature by now after using table of values for so long in pre-algebra and Algebra 1. But I love the transformation rules, or vertex form, because it's kind of like a shortcut. It's a quick way to graph your function without having to make a table of values. So sometimes we like things that help us cut down on the amount of work we need to do. Now, when we have a transformation, we are saying that we can move a shape on the graph. We can change its size or move its position, and an absolute value graph is always a V, so we're going to be allowed to change the position, like move the vertex around, and we could also change its size. We could make it a skinnier V by having a vertical stretch. We could make it more of a flattened out V by giving it a vertical compression or shrink. Okay, we can make it go down by reflecting it. These are all types of transformations that we're going to come to recognize by just looking at the equation. So we're going to start with the parent function of an absolute value function. Now, a parent function is the simplest way a function can be written. And for absolute value, we've seen this before, it would be f of x equals just the absolute value of x. So notice this is the most simple way that we could write the absolute value function, because only x is inside the absolute value bars and we do not have any numbers being added or subtracted inside our absolute value bars, outside our absolute value bars, and nothing's being multiplied to it. This is as simple as we could make it. When we graph this parent function, it has a vertex that is at the origin and increases by 1 over 1 on either side. Basically, it has a slope of 1. So it's a nice V that's increasing, but with the same slope on either side. It's symmetrical. It is wonderful. Okay, so this is our parent function. And I'm going to leave this parent function in blue. Now what we have on the left is 2 is being added, subtracted inside our absolute value bars. It's being added and subtracted outside the absolute value bars. 2 is being multiplied outside the bars. 1/2 is being multiplied outside the front of the bars, and we've added a negative. So basically we're doing all these different things with 2, and we're going to show how it transforms our parent function that's in blue. So I'm going to start with doing number 1, and we have f of x equals the absolute value of x plus 2, and this is going to be done in green. Okay, so I'm going to show how this transforms our graph. This would have a vertex actually at -2, 0, and it's going to increase by 1 over 1 on either side. So notice it has the same slope, it's the same size, but its vertex is in a different location. How has the vertex moved? Well, our vertex has moved from being at 0, 0 for the parent function. Okay, so let me write that up here. Vertex for our parent function is always 0, 0. And it's moved 2 spaces to the left, so now our vertex is -2, 0. And everything else kind of is looking the same about this V. So if I had plus 2 inside the bars, why did it move left 2 and not right 2? Now if you remember, the rule is you take what is inside the bars, set it equal to 0, and solve for x. So that would mean subtracting 2, which would give us x equals -2, placing the x value of our vertex at -2. So interesting, right? When we are adding a number inside our absolute value bars, our vertex actually shifts left that many spaces. Now next, on number 2, we have the absolute value of x minus 2 inside the absolute value bars. Okay, I'm going to do this in pink. Now, when I graph this, if I take the inside, x minus 2, set it equal to 0, and solve for x, I'm going to get x equals +2. And then I plug it back in, I'm going to get 0 for y. So my vertex is actually going to be at 2, 0, and then it's still going to have a slope of 1 over 1 on either side. Okay, so notice, again, it's the same size and shape, but it's vertex has been shifted 2 spaces to the right. Okay, so it went right 2 spaces. So again, we had a minus a 2 inside the absolute value bars, and it actually moved our vertex 2 spaces to the right. So interesting. These are going to all apply into our rules later on. But so plus means it moves left, minus it means it moves right. That's our vertex. Now I wish I could show this with a graphing calculator. In class we are going to do this more hands-on with a graphing calculator, and we won't have everything just being displayed on the same graph. And I've tried really hard with the technology, but it keeps messing up to let me do it with the app I'm using to record the videos. So if you are by chance watching this video, just bear with me. Hopefully you can be able to make it in class at some point so that I can show it more clearly. But on number 3, we have the absolute value of x, and then we are adding 2 on the outside. Now my x5, my vertex, is just going to be 0 because that's the only thing inside the absolute value bars. And when we plug it back in, we're going to get 2 for y. So we're at 0, 2 for our vertex. So 0 for x, 2 for y. Okay, up 2 is now right here, and then we are going up 1, right 1, up 1, right 1. On either side, up 1, left 1. So this is being done in purple. So again, which one was my parent function? If you remember, my parent function was done in blue. So what happened here is it moved, my whole vertex went up 2 spaces because we had this addition of 2 on the outside of the absolute value bars. So when we're moving left and right, that's inside the bars with the x because the x does move left to right, but we do the opposite of what the sign is. When it's on the outside of the absolute value bars, we're doing a vertical transformation, and we do exactly what the sign says. So when we have on number 4, the absolute value of x minus 2, okay, right here, I'm going to do this in yellow. The x value of my vertex would be 0. That's the only thing inside my bars. When I plug 0 in for x, I'm going to get negative 2. So 0, negative 2. That's my vertex. We're going to go down 2 and then increasing by 1 over 1 on either side. Okay, so here we go. Look at all these v's. They're all the same size, and they're all the same shape, but their vertexes have been moved all over the place, and this has been down 2 units because of that minus 2 on the outside. Now I can't really show it here, but I'm going to just do it here on the side. When we have this 2 times x inside, the 2 is on the outside, and then just x on the inside, this is going to be a vertical stretch. It's actually going to make, we have a steeper slope, so it's going to make a bit of a skinnier v. We'd have a vertex at the origin. And on number 6, when we have 1/2 then the absolute value of x, it's going to shrink it, and we're going to get a bit of a flattened out v. Now what happens when we say negative absolute value of x? Now because that negative sign's on the outside of the absolute value bars, whatever comes out, even though it was positive briefly, when it comes out, it's going to turn back to negative, and what that does is it turns our arrows, or turns our v upside down so that our arrows are going downwards. So we will see all these transformations. We're going to write the rules down on the next slide, and hopefully it's going to give us shortcuts to be able to make these graphs more quickly. So on this next part of our notes, we have our transformations guide. So a little shortcut. What we have starting at the top, it says f of x plus h, meaning that whatever is inside the parentheses or absolute value bars, inside of those bars with x, and it's being added, okay, that's the h value represents the number being added, we're going to shift left that number of spaces. So plus means to move left, and let's draw an arrow going to the left. Now whatever is inside the bars with the x, and we are subtracting it, so we're going to say f of x minus h, means that we actually go right that number of spaces. So minus means to move right. So when it comes to being inside with the x, it's actually the opposite of what the sign says, and that's because it was the part that got set equal to 0 and then solved, so it always takes on that opposite sign. Now we have f of x, okay, that x part that's inside parentheses. The x part is what moves left to right, but what's on the outside of the bars or parentheses, if we have those, is the k value. Now the k value represents the vertical shift. So if we have a number outside our absolute value bars and it's positive, we are shifting up that amount of spaces for our vertex. And if we have a number that's being subtracted outside the bars, we are shifting down that number of spaces. So that's our rule for the vertex as far as that goes. Now we have dilations as well. If we have a number that is where its absolute value of that number is greater than 1, we are going to get a vertical stretch. Okay, so this is a number that is being multiplied to our absolute value part of the function. Its absolute value is greater than 1. And we say absolute value because a negative sign does something different. Vertical stretch kind of makes it all skinnier. Our V's getting closer together. It's like it's been stretched from bottom to top, piece of taffy, just getting really like long and skinny. Okay, so a number larger than 1 basically stretches it out longer, taller. Now, if we have a number that is being multiplied into our absolute value bars that is between 0 and 1, so this should have been written as this. 0 is less than the absolute value of a, which is less than 1, meaning a fraction that is smaller than 1, then we're going to get a vertical compression or shrink. And that means it's kind of been flattened out so that our V's kind of looking something like this. It's like, or really flat, like, okay, so that's a vertical shrink or compression. Okay, it's getting closer to being more like a flat line than a V. Okay, and then the last thing we have is if we've got this negative sign. Okay, if we've got a negative sign in front of our absolute value bars, you would have noticed this as we've graphed in other lessons. What this does, it reflects our V across the x-axis so that it's opening downwards. Both our arrows are going down, so downward facing V. So this is our transformations guide, and we're going to practice it more throughout these notes. So now that we've gone over that transformation guide, hopefully you still have your notes out and you've written that down. We're going to go A through F, and we're going to say how the parent form, our parent function, has been transformed. So if you're looking at problem A, we have f of x equals the absolute value of x minus 5. So I'm looking, our parent function, again, is f of x equals just the absolute value of x. So you think, what has been made different from this function to this function? Well, we have the minus 5 inside our bars. So to me, I'm thinking this minus 5 is inside the absolute value bars. It's with the x essentially. So that means it's either a left or right shift. And because it says minus, I'm thinking, oh, okay, if this one's doing the opposite. Minus 5 actually means that this was moved right 5 spaces. It does the opposite if it's inside the bars. Okay, now B, we have a different function. We have the f of x is equal to the absolute value of just x, and then we are adding 9 on the outside. So this plus 9 is outside the bars. If it's outside the bars, it's not left or right, it's a vertical shift, and this one does exactly as the sign says. So this is going to be going up, and what we're going up that many spaces, so we're going up 9 units. All right. Now on part C, we have f of x is equal to negative and then the absolute value of x. This negative sign is outside the bars. And anytime you see a negative sign like leading a function, or whether it's quadratics or absolute value, if it's in front, that's going to be a reflection across the x-axis. It's going to like turn it and make the arrows go down. So we're going to say reflection across the x-axis. Okay, so that these negatives always like turn things around. Now on part D, how have we changed from just being absolute value of x inside? Now we have 3 on the outside times the absolute value of x and then a minus 2. You can have more than one transformation. So this minus, or this 3 on the outside, okay, it's larger than 1. Okay, it's an absolute value of 3 is 3, and that number is larger than 1. So what that is, it's a stretch. So we would say that's a vertical stretch. And we would say like by 3, vertical stretch by 3. We would put the number. And then what's the minus 2 doing? Well, it is outside the bar, so it can't be left or right. It's not inside by the x. So that would be vertical movement, and it would be moving our vertex down 2 units. Okay, so we had 2 transformations there. Okay, vertical stretch of 3 and moved down 2 units. Okay, on part E, we have added 1/4 on the outside and then x plus 6 on the inside. So we have 2 things that have been added to the x that is normally just inside when it's a parent function, so that means we also have 2 transformations. Now 1/4 is a fraction that is smaller than 1. Now remember, sometimes we have fractions that have a value larger than 1. Like if I had 7/2, that's a fraction larger than 1, so that would be a stretch. But 1/4 is smaller than 1, so this is a vertical compression or shrink. So we're going to say vertical compression, and I don't mind if we use or shrink, whichever one you like best. We would say of 1/4. And then this plus 6 is inside the absolute value bars with the x term. So because it's inside with the x, I remember x moves left to right. And I also remember that x's do the opposite. So plus means it's going left 6 units. So that's the thing we have to remember. The x's do the opposite. Okay, and then on our last one, F, I'm looking for how many changes I've had to just having an x inside the bars. So I have a negative sign on the outside, a plus 7 inside the bars, and a minus 2 outside the bars. I've got 3 things that were added, so I'm having 3 different transformations, okay? 1, 2, 3 things. So the negative sign was a reflection across the x-axis. Okay, it turns it so the arrows are going to be going down. Okay, that's one change. Plus 7 inside. Okay, inside is left to right. Plus means do the opposite, so we are going left 7 units. And then we have this negative 2 on the outside the bars. Okay, at the end is our vertical shifting, so negative means we are going down 2 units. Okay, now we're going to apply all of this to how we could identify what the vertex is and then the slope, and then graph all of these functions without using a table of values like I had mentioned before. So now that we've talked about all those horizontal and vertical shifts and the other transformations, we can use those horizontal and vertical shifts to describe the location of the vertex, okay, without using like an equation and without using a table of values. So the vertex form, okay, or formula for an absolute value function is written here in blue. It's f of x is equal to a times the absolute value of x minus h, all that's inside the bars, and then plus k on the outside. So a, h, and k all represent like numbers in the equation, where h comma k represent the vertex. Now notice it was negative h inside, and outside it says positive. So that represents having that sign change whenever we had, like, you know, if it said plus 2 with the x plus 2, that really meant minus 2. And if it was x minus 5, it really meant plus 5. It represents changing the sign on whatever number was inside with the x. And then the k, notice it's positive here and it's positive there. So that sign stays the same. Okay, so h and k, the number with the h number is the x value of the vertex, k is the y value of the vertex. And then it says here that a is the slope on the right side and negative a is the slope on the left. Now usually we use m, okay, for slope, but here for these we're saying a. Okay, so you could think of it, a and m, as being like the same type of thing. But if you have a number on the outside of the absolute value bars, that represents a slope. And if there's not a number there, that's like having 1. Our slope is 1 over 1. So these all give us a little bit of shortcuts in our graphing. Okay, so on example number 1, I have the function f of x is equal to the absolute value of x minus 2, and then outside of that we are subtracting 4. I'm not going to use a table of values. I'm going to use my vertex rules. So my vertex will always be an x and a y value. Okay, now thinking about our absolute value vertex form function, we have the absolute value of x minus h plus k and a on the outside. Okay, that's what we had on the last slide. And we said that h comma k is the vertex. So which number represents h? It's the number that's inside with the x, but we take the opposite sign. So that value would be this minus 2. When I take it out, it always has the opposite sign. It's going to be a positive 2. Okay, so because h comes first, and then k is the y value. K is what is outside the bars, and we leave it with the same sign. So that would be negative 4. So right away, just by looking at it, the only two numbers up there were negative 2 and negative 4. We just made the one inside the bars positive. So 2, 4, 2, negative 4 is my vertex. I'm going to go right 2 and down 1, 2, 3, 4. Put my first dot. Okay, did that without having to use an equation. Now, slope, okay, is that a value. It is represented by the number that is out in front of the bars. And notice I don't have one, so that means I have a slope of 1, and then we could put that over 1. And that's moving to the right. Okay, so as I move to the right, I'm going to go up 1, right 1, up 1, right 1, up 1, right 1. And we have learned by now that, absolute value makes a V, which is symmetrical. So if we were going up 1, right 1, on the right side, we need to do the opposite, go up and left to the 1, because we need this to be symmetrical. Okay, so here we go, and connect your points. We get to use solid lines because we're using an equal sign. But can you see how from our first point to the next, we are going 1 over 1 every time? So we're done. And again, that was just by looking at the equation and using our transformation rules, which we will keep practicing. Okay, on number 2, our function is f of x equals 3 times the absolute value of x plus 5. So again, I'm kind of comparing it right here to the vertex form, like that base formula for that. And I'm remembering that vertex is h and k values. And so if I need a reference, h is a number that is inside with the x. So that is a positive 5 inside the bars. And when we take it out to make the vertex, we take the opposite sign. So that's going to come down as negative 5. Now, the y value of the vertex is k. Now, that is what's being added outside the bars. Okay, it should be located in here. And notice I don't have anything. So that's like saying plus 0, making the y value of our vertex 0. Okay, so the vertex, we're saying h and k instead of x and y, but it does mean the same thing as an x and y value. So negative 5 and 0 is left 1, 2, 3, 4, 5, and it's staying there. So I already have my vertex. I'm going to be symmetrical about that point. But what is my slope? Okay, slope is the a value. A is the number on the outside of the bars, so that would be 3. And we always think of slope as a fraction, even if it's not given as one. So that'd be 3 over 1. As we work to the right, we are going to go up 3 and right 1. So 1, 2, 3, right 1. 1, 2, 3, right 1. Do at least a couple points. And then we are going to make that symmetrical. So we're going to go on the other side to the left. We're going to go up 1, 2, 3 still, but go left 1 each time. 1, 2, 3, left 1. Okay, so now I have a nice symmetrical V, and I connect all my points. Again, pretty fast, and I didn't have to use a table of values. Okay, number 3, we have the function f of x equals 2 times the absolute value of x plus 1, and then subtracting 2. So if you'll recall, to graph these, and when we're using the vertex form shortcut, we need the vertex and we need the slope. So a vertex is an ordered pair. Okay, the vertex is called h and k. Again, it's the same thing as like x and y. The x value is the h, the k value is the y value in this situation. So I get the x value of my vertex by taking the number that is inside with x and switching the sign to the opposite. So I get negative 1. The y value of my vertex comes from what is on the outside of the absolute value bars to the right of it, and that's a -2, and we keep the sign the same. That's just the way it is. That's the rule. Sooner you learn it, the better. So we're starting at the origin, we go left 1 and down 2, plant our dot. Now to continue and to make this a V, we need the slope. Again, it's using A for slope instead of M, but that would be the number on the outside of the bars. And the number on the outside in the front that's touching it, that's being multiplied to it, is the number 2. So I would think of this as 2 over 1. So we are going up 2, right 1 from our vertex. So we start at my red dot and we're going up 2, right 1, up 2, right 1. And let's do enough so that we can get a good shape of the V. We need to make this symmetrical, so we're going to go back to the red dot, back to the origin, and we're going to go up 2 and left 1 from that point. Up 2, left 1. Okay, when we've got enough points on there, we just connect our lines. And we are done. We have our absolute value function. For number 4, we have f of x is equal to negative, and then the absolute value of x minus k. Now, as soon as I see this negative sign on the outside, I should be thinking that I have a V that's going downwards, okay? So we should be expecting that as we graph. And let's look. What we need from the function is we need to first get the vertex. We need an x and a y value. So we're making a coordinate that we are symmetrical about. So remember, the x value comes from the number that is inside the bars with the x. Inside we have a -6. When it comes out, it's a +6. That's the rule. Take the opposite sign. The y value from the vertex is the k value. What is being added or subtracted after we have the bars to the right of it? And notice that this is kind of like an empty spot. We don't have anything. So because of that, that's like saying +0. So that means our k value is 0. Our vertex is at 6 for x, 0 for y. So we're going to start the origin and go right 1, 2, 3, 4, 5, 6 spaces and put our dot. Now we need our slope. Okay, our slope, again, I'm going to keep saying this is an a value. A is what is out in front being multiplied on the front left side of the absolute value bars. And that is a negative sign, which I would think of as -1. And then over 1. When we have a negative slope, that's telling us to go down that many spaces for the numerator, but we still work to the right. Okay, when we get the slope, that original slope is telling us always how we're moving, okay, to the right. So we are going to go start at our vertex, this red dot, and we're going to go down 1, right 1, down 1, right 1. Okay, I'm kind of at the end of the line here. So I'm going to go back to my vertex, and I'm going to go down 1, left 1, because we always are making this symmetrical. Okay, and then connect your points. And voila, it's done. Easy as pie. Okay, on number 5, we are given the function f of x equals 2/3 and then times the absolute value of x plus 1 minus 1. So notice I've got 3 extra things that were added to like my parent function here, but we're still finding the vertex first by taking that h and k value. Remember, h and k mean x and y. I'm going to keep saying that. The x value from the vertex comes from the number that's inside the bars with the x. It's +1 inside, so we change it to -1. The k value or the y value for the vertex is what comes after, and that's also, okay, it's -1 and it stays -1. So our vertex is -1, -1. That means left 1 of the origin and down 1. Plant a dot. And then we need to find our slope. Again, slope is being used by the letter A here, and that is the number being multiplied to the front of the absolute value bars, which is 2/3. That's our A value. Okay, now I like it when it's already a fraction because it's already set up as rise over run. We are going up 2, right 3 because our slope is originally telling us how we're moving to the right. So going to my green vertex dot, I'm going to go up 1, 2, and then right 1, 2, 3 spaces, put a dot. Up 2, right 1, 2, 3. Okay, let's now mirror that and work to the left. I'm going to go up 2 and left 1, 2, 3, plant a dot. Up 2, left 1, 2, 3. Okay, nice and symmetrical, and we're done. So the really important thing is to remember is to take the opposite of what is inside the absolute value bars for the x value of your vertex. Okay, number 6, we have f of x is equal to negative 3/4 times the absolute value of just x plus 7. Okay, so my vertex, my x and y values, which is really the h and k values. Okay, now the x value of the vertex is what is being added or subtracted inside the absolute value bars after the x. And notice it's just x. We don't have plus or minus anything. And when that's the case, then 0 is the x value of our vertex. H is actually 0 here. It's not there, so it is therefore 0. The k value, it is what's being added to the right of the bars, and that's a plus 7. So our k value is 7, making our vertex 0, 7. We stay at the origin, but then move up 1, 2, 3, 4, 5, 6, 7 spaces. Now our slope, again, that is what is out in front of the bars, multiplying at the very front, and that is negative 3/4. So again, negative means move down that many spaces in the numerator. The denominator is how many to the right we go. So we are going down 1, 2, 3, and to the right 1, 2, 3, 4. Plant a dot. Down 1, 2, 3, to the right 4. We will mirror that on the other side by going down 3, left 1, 2, 3, 4, and down 3, left 4. Can you tell that this V, because not only was it going down because of the negative sign out in front, but 3/4, that's a fraction less than 1. It actually kind of like compressed it a little bit. Our V is wider, a little bit fatter than normal. So that's what our fraction did there. Okay, on number 9, I'm going to skip to this one. I think I've tortured you guys enough with piecewise functions. We're going to see how we can still use our vertex and transformation rules when it comes to using absolute value inequalities. That's where we have our dotted and our solid lines and our shading above or below. But using the vertex form works in the same manner. To get the vertex, I'm getting a coordinate. We're getting our x and y value from looking at the equation. The x value of the vertex comes from what is inside the absolute value bars with x. I have a positive 4, so we take it out as a negative 4. The y value of the vertex is what is outside the absolute value bars. That's a negative 6, and it stays the same. So negative 4, negative 6 is my vertex. We're going left 1, 2, 3, 4, down 1, 2, 3, 4, 5, 6. There's our first dot. Our slope is still like the a value. It is what is being multiplied to the left just in front of the bars. And I don't have a number there. So that tells me it is 1, and we're going to put it over 1. So up 1, right 1 of our vertex. So we're going to start this blue dot, go up 1, right 1, up 1, right 1, okay, on either side. And mirror that. Okay, but remember, whenever we see that we have an inequality sign instead of an equal sign, we're going to stop before we connect our points, and we're going to decide 2 things based off the sign. So the sign that we are using is a less than or equal to sign, okay? Less or equal. That's what I'm going to just write, that little shorthand. Okay, now that tells me 2 things. It's going to tell me if we're dotted or solid. Because it has the or equal to bar, that means that we have a solid line. So I'm going to connect all these dots, and I'm going to continue it all the way out. Okay. The next thing it's going to tell me is if I'm shading above or below the line. Less to me, okay, less means get lower. To me, that's like going down. So that means to shade below. So I'm going to say shade below. And we're shading below the vertex. So keep in mind, my vertex is here. To shade below it is everything underneath that point. So it's all of this business down here. Okay, so that's, again, the same transformation rules. I was able to get my line on here, my V on here very quickly by using those transformation and vertex rules, and then using my knowledge about the sign to connect my points, make it solid, and shade below. Okay, last one, number 10. I have the function f of x is greater than negative 2 times the absolute value of x minus 5 and then plus 4. Again, the vertex is a coordinate. Okay, we need an x and a y value. The x value of the vertex is from the number that's with the x inside, and when it comes out, we change its sign. So this would be positive 5. because we had a minus sign inside. And then the y value comes from what is outside being added to the right of all that, which is positive 4. My vertex is positive 5 and positive 4 for y. 5, 4. 1, 2, 3, 4, 5, up, 1, 2, 3, 4. All right, my slope is the a value. The a value is the number to the left being multiplied in front of, like, into the bars, which is negative 2. I put it over 1 if it's not a fraction, which means to go down to right 1. Okay, and again, because 2 is like, okay, that a value, we could also think, what's the absolute value of negative 2? It's 2, which is greater than 1. So this is going to kind of give it a vertical stretch as well. It's going to make it skinnier. And the negative is what makes it go down. So we're going down to right 1, down to right 1. And then we mirror that, go down to left 1 on either side. Okay, and I'm going to stop right there because I noticed that I had an inequality sign, not an equal sign. So our sign is like this. That's a greater than, okay? That's just a regular old greater than sign, not or equal to. So it tells me that this line will be dotted, not solid. So I'm going to use little dashes or dots to connect my points. And then it also tells me which way to shade. Greater than, to me, the numbers are getting bigger. That's going up. So I'm looking at my vertex and I'm shading everything above that. So above would be everything on this side of my V. We'll shade it in. Okay, get to know your transformation rules. It will be on the quiz that we have coming up. The sooner you get to know them, the faster you will be at graphing, and the more it will help you when we get to quadratics. Those are our parabolas, and those are coming up pretty quick.